want to do some problems from section 2.4 and section 2.5 to kind of go over things we've talked about this week. We've also talked about some stuff in section 2.6, but we'll see more of that stuff next week. So in this problem set, I just want to do things out of 2.4 and 2.5 and do some problems out of the book. So out of section 2.4, I'm going to start here with number 30. And so this is probably out of the book where the exercises start for section 2.4. And embarrassingly, I didn't write down the page number, but you can find these problems in the textbook with section 2.4. Let's just do problem number 30 here. The instructions are just divide using synthetic division. Problem number 30 says x to the 7th minus 128 all over x minus 2. So we're going to set up the synthetic division. 2 is going to go in the box because I'm dividing by an x minus c. The thing after the minus goes in the box. Now a bunch of leading coefficients. Well, I have an x to the 7th, no x to the 6th, no x to the 5th, no x to the 4th, no x to the 3rd, no x squared, no x, but I do have a constant term. That's a lot of placeholders. Let's make sure I did that right. 7, 6, 5, 4, 3, 2, 1, 0. Always counting down by degrees. All right, so now it's just up to us to do the synthetic division. To bring down the 1, we multiply. We add, we multiply. We add, we multiply. We add, and I kind of see what's going on here. Feeling pretty good about this now. Oh, and I get a remainder of 0. Well, that's really cool. But we weren't just supposed to find the remainder, we were supposed to divide. Well, we got a remainder of 0, which means we just get a quotient, right? Plus 0, right? So the quotient here, x to the 6th, plus 2x to the 5th, plus 4x to the 4th, plus 8x cubed, plus 16x squared. You know it's a good problem when you run out of board. 16x squared plus 32x plus 64. And then we'd usually write plus 0 over what we were dividing by, but anything divided by 0 is, well, 0. And that's what a remainder of 0 means. We have an even, we've divided this evenly. X minus 2 goes into this evenly. So that's pretty cool. All right, so that was number 30. Let's do one more synthetic division problem. I hadn't planned to do one more, but now I'm just kind of feeling like we should. So let's go back up here and do number 26. Number 26 wants me to divide x squared minus 5x minus 5x cubed plus x to the 4th by 5 plus x. All right, well, I see what the author's doing here, right? He's written this down in kind of a weird way where the leading coefficient's is not out front, right? It doesn't look like a leading coefficient. So let's rewrite this so that each part, the dividend and the divisor, are kind of written in the way that we usually think about them, with the highest power of x out front and then just descending by degree. All right, so I'm really dividing x to the 4th minus 5x cubed plus x squared minus 5x by x plus 5. So minus 5 goes in the box, and then I have 1 minus 5, 1 minus 5, and 0, because I need a constant term, right? Start with degree 4, 4, 3, 2, 1, and the degree 0 part has to be 0. It's a very easy to forget placeholder when it's at the end. All right, let's do the synthetic division. All right, so now I got to multiply minus 5 by 51, and I'm totally going to do that in my head. 51 times 5 minus 5 is minus 255. All right, so now I have minus 260 times minus 5. I have a quotient and a remainder, but I was asked to divide. All right, so I'm going to write my original problem down like it was a quotient, because it is. And this fraction is then equal to a quotient. All right, so let's see what the quotient is here. Well, that would start with an x cubed. So 1x cubed minus 10x squared plus 51x minus 260. All right, just looking at those coefficients, right? And then plus the remainder over what we were dividing by. All right, so there are two nice happy synthetic division problems. Let's see what we have to deal with next. Well, the next problem I want to deal with actually makes us do synthetic division again, but wants us to use the remainder theorem. So I have number 39 here circled. And hey, this has a page number. This is on page 366, which makes me guess that last page was page 365. Well, that was a little late, but now you know. Use synthetic division and the remainder theorem to find the indicated function value. Well, here in number 39, we're given f of x is 2x to the fourth minus 5x cubed minus x squared plus 3x plus 2, and we're asked to find f of minus 1/2. All right, well, what the remainder theorem says is that when I do the division, f of minus 1/2 is going to be my remainder. Minus 1/2 goes in the box, and then I just do my synthetic division in the usual fashion. So I bring down that 2. 2 times minus 1/2 is minus 1. I get a minus 6. Minus 6 times minus 1/2 is 3. Add those together, I get a 2. Times a minus 1/2 is a minus 1. Get another 2. So I get another minus 1. And finally, I get a 1. So f of minus 1/2 is equal to 1. That's what the remainder theorem says. All right. Well, I trust the remainder theorem. I feel very good about it, but I'm worried that you don't, that you haven't seen, as many examples as maybe you will as you go through the homework. So what I'm going to do is I'm going to type the function in my calculator. And I'm going to go into the table feature here. I'm going to clear out what I have in there. I'm going to plug in a minus 1/2, and I hope I'm going to get out a 1. Hey, there it is. I plug in a minus 1/2 and I get out a 1, so now I feel even better about it. The remainder theorem does seem to work here. All right, so that was number 39 on page 255. A nice application of synthetic division. Next up, I have some problems out of section 2.5. And I don't have the page number here either, and I don't have a second page to even guess what it would be off of. So just find the problems in section 2.5, and I want to start off with number 12. Number 12 gives us a rational function, f of x equals 2x cubed minus 5x squared plus x plus 2. And the instructions are to list all possible rational zeros using the rational roots theorem, use synthetic division to test the possible rational zeros and find an actual zero, use the quotient from part B to find the remaining zeros. All right, well, we're not stuck in the 17th and 18th century, so we're going to not just try randomly all the rational zeros. We're going to use some 20th century technology here to help us out, even though we're in the 21st century. So, the rational roots theorem says that if I have a rational root, it's in the form of p over q, where the p's are factors of this term, of the constant term at the end. Well, the only factors of 2 are plus or minus 1 and plus or minus 2. And the q's are factors of the leading coefficient. So again, plus or minus 1 and plus or minus 2. And now I just have to think about how I can divide those things. Well, I'm going to divide each p by each possible q. If I divide plus or minus 1 by a 1, well, I'd get plus or minus 1. If I divide plus or minus 2 by a 1, I get plus or minus 2. And then if I divide 1 by that 2, I could have a plus or minus 1/2. And if I divide 2 by 2, I get plus or minus 1 again. So it's only these 6 values. These are the 6 things I have to worry about, maybe being rational zeros. Well, I don't want to just blindly try things. So I'm going to type the function into my graphing calculator, 2x cubed and I'm going to look at a graph. And, well, looking here, I think maybe there's a 0 at -1/2, maybe there's one at 1, maybe there's one at 2. Maybe I wouldn't have had to try very hard, but I'm going to choose 1 to start because that's kind of the easiest thing to do synthetic division with. Though none of those numbers seem particularly challenging. So 1 goes in the box, and I do my synthetic division in the usual fashion. Hey, that is a 0. The first one I tried using the graphing calculator helps me out. Now that being said, I'd probably tried 1 if I was just randomly guessing things, but I feel really good about this. That also helps me get started factoring. Because the division algorithm then says my function is equal to what I was dividing by, x minus 1, times the quotient. Plus the remainder, but the remainder is 0, and that's the whole point, right? With the remainder 0, I know I've divided evenly, which means I have a factor. Okay, so here I have a quadratic part. Well, let's see. I could try to use a quadratic formula to find the zeros, or I could just factor it. Let's factor it. All right, so I need a difference of -3, so I'm thinking a -2 goes here, and a +1 goes here, and you can check it out, and everything works out fine. So my zeros, well, they're 1, and I already knew that, -1/2, and 2. And it turns out all of my zeros actually appeared on this list, right? I had the +1, a -1/2, and a +2. One thing to point out is not all the possible rational zeros are actually zeros. Those are possible rational zeros, not the actual zeros. And the other thing to point out is all of my zeros don't actually have to come from that list. I could have irrational or complex zeros. But that gets us through the end of number 12 here. Next up, I wanted to do number 29, which actually has us build a polynomial from its roots. So I'm going to summarize problem number 29 here, and then we'll read the directions. All right, the instructions here. Find an nth degree polynomial function with real coefficients satisfying the given conditions. If you're using a graphing utility, use it to graph the function and verify the real zeros and the given function value. And I guess the one thing I haven't written down yet is that f of -1 is equal to 20. All right, well, we don't have any real zeros. We were just given 2 complex zeros. We're told the degree is 4. And so what we know is a polynomial is equal to some constant a times a product of linear factors that come from the zeros. And to be degree 4, it means I have to have 4 linear factors. So it's like I only have 2 zeros and I'm missing 2. But then I remember that if a plus bi is a complex root, then a minus bi as complex conjugate also has to be a root. So if 0 plus I is a root, then 0 minus I also has to be a root. If 3i is a root, then 0 minus 3i also has to be a root. So we actually do have 4 zeros if we use the conjugate pairs theorem. All right, well, I need to figure out what a is. I've got an expression for my polynomial, but I'm going to multiply these things together. And I'm going to do it in pairs because, well, I recognize what's going on here, right? This kind of format here, I'm going to end up with like a difference of squares kind of thing. X times x is x squared. Minus ix plus ix, the middle terms cancel, and I end up with a minus I squared. Well, minus I squared is just a plus 1. And here on the end, x times x is x squared. The middle terms cancel, and I'm left with a minus 9i squared, but that's really just a plus 9. All right, well, I can't help myself. Let's go on and multiply these two things together. X squared times x squared is x to the fourth. Plus 9x squared and one more x squared, I get 10x squared plus 9. Now all I have to do is figure out what a is. And the only bit of information I haven't used yet is that f of minus 1 is equal to 20. So y is equal to 20 when x is minus 1. All right, so let's see, I have 20 equals. And in this I'd have 1 plus 10 plus 9 more. So let's see, 1 minus, I was right the first time because I forgot to write that squared down. See, I knew that was going to be a 1. All right, 1 plus 10 plus 9. So I have a times 20. And a has to be 1. All right, that lets me write down what my polynomial is. F of x equals 1 times x to the fourth plus 10x squared plus 9. Well, the instructions ask me to use my graphing utility to verify any real zeros. No point to doing that here. There are not going to be any real zeros. So there's my nice, happy final answer.